Today we're tackling, well, one of the boldest ideas in modern physics, quantum computing. Imagine machines that could unlock breakthroughs in, everything from designing new materials to discovering life-saving drugs. Sounds incredible, right? But here's the profound challenge, the core paradox. These incredibly powerful devices are also um, exquisitely fragile. The moment we step into the bizarre world of quantum mechanics, with superposition and entanglement, we also open the door to something called decoherence. Think of it as the irreversible loss of that precious quantum information. It fundamentally limits how long a qubit, our basic unit of quantum information, can reliably process data. We call this the coherence time. And for solid-state qubits, which are, leading candidates for building these machines, the environment isn't some distant abstract thing. It's the very crystal lattice the qubit is embedded within. Within that lattice, the biggest troublemaker for quantum coherence is something called phonons. You can kind of picture them as the quantized vibrations of the lattice, tiny restless packets of sound energy constantly interacting with our qubit. These interactions are bad news. They cause energy relaxation, which we track as T1, essentially the qubit losing its energy. And they also cause phase loss or dephasing, called T2, scrambling the delicate quantum state. The conventional solutions to this problem are extreme. We're talking super cold, cryogenic cooling, often down to millikelvin temperatures, just a tiny fraction of a degree above absolute zero. Really cold. But what if there was a completely different approach? What if instead of fighting these phonons with extreme cold, we could somehow make them, well, not exist? What if we could erase the eraser? That's our mission today. We're taking a deep dive into a radical, incredibly counterintuitive hypothesis from recent research, operating a qubit in a host material so extreme that the very concept of a well-defined phonon becomes meaningless. We'll unpack the underlying physics, explore the supposed benefits, critically examine the fundamental flaws that quickly emerge, and confront the immense engineering realities. It's a journey into an audacious and perhaps deeply flawed idea that still teaches us profound lessons about quantum mechanics and, well, the nature of reality itself. Okay, let's unpack this. We start with the fundamental building block of the lattice's noise, the phonon. Now, it's important to remember that a phonon isn't a fundamental particle like an electron or a photon. It's a quasi-particle.
Right. It's an emergent concept. It comes from a simplified theoretical model of the crystal lattice.
The harmonic approximation, where atoms are like masses on perfect springs.
Exactly. And it's useful for some things, but it's fundamentally limited. It's really where that approximation breaks down that things get interesting.
How so?
Well, in the real world, interatomic forces aren't perfectly linear like those ideal springs. There's this deviation called anharmonicity. We account for it by including higher-order terms in our models. And these terms, they're the key. They lead to phonons actually interacting with each other.
So they're not just independent vibrations.
Not at all. And these interactions aren't minor corrections. They're responsible for fundamental things we see every day, like thermal expansion, finite thermal conductivity, and crucially for us, finite phonon lifetimes. A phonon in a real crystal isn't stable. It can decay into other phonons, like a ripple fading out.
Okay, so that finite lifetime, the anharmonicity, that's what makes the lattice noisy for a qubit.
Precisely. That's where the delicate quantum state gets corrupted.
But how does this noise actually couple to different types of qubits? Is it the same mechanism for all of them?
Oh, that's a great question. No, it differs quite a bit. For spin qubits, say in quantum dots, the coupling is mostly indirect. It's mediated primarily by something called the spin-orbit interaction. Phonons wiggle the electron's orbital motion.
Through strain and electric fields.
Exactly. And spin-orbit translates that wiggle into a fluctuating magnetic field acting on the spin. This causes both energy relaxation, T1, and for certain phonons, like piezoelectric ones, T1 can depend very strongly on the magnetic field, like B to the power of 5.
Wow, B to the fifth.
Yep.
That's incredibly sensitive. Tiny magnetic fluctuations would cause huge error.
It's a massive hurdle. And of course, it also causes dephasing, the T2 loss.
Okay, what about superconducting qubits, like transmons?
For transons, it's often a kind of two-step process, like quantum telephone. The qubit first interacts with these microscopic material defects, tunneling two-level systems, or TLS.
Often in the oxide layers, right?
Yes, exactly. In the Josephson junctions, usually. So the qubit excites a TLS, and then the TLS rapidly dumps its energy into the substrate by emitting a phonon. And this second step is incredibly efficient because the phonon bath, well, it just has a much, much higher density of states than photons do. Maybe 5 orders of magnitude higher. It's a super efficient energy sink.
So the TLS acts like a funnel for noise into the lattice.
You could put it that way. And we also have to worry about high-energy phonons, maybe from cosmic rays hitting the chip. They can directly break Cooper pairs in the superconductor, another error source.
Okay, so different qubits hear the phonon noise differently. You mentioned T1 and T2. We often hear about noise spectral density, S of omega, S of... What is that exactly, and why is it so central here?
Right, so it's basically a map. It tells you the power, the intensity of the environmental fluctuations at any given frequency. Think of it like an audio equalizer for noise.
Showing where the noise is loudest in frequency terms.
Exactly. And it matters profoundly because different decoherence processes listen to different parts of this noise spectrum. T1, energy relaxation, is sensitive to the noise right at the qubit's transition frequency. That's where energy exchange happens most easily.
It makes sense.
But T2, pure dephasing, that's the loss of phase coherence from slower fluctuations that's sensitive to S. The low-frequency noise, the sort of background rumble.
Okay, low frequency for T2, qubit frequency for T1.
Right. And the core idea of this phonon-less strategy isn't just about reducing the number of phonons, like cooling does. It aims to fundamentally reshape S, a qualitative shift, not just quantitative.
Reshape the noise. Okay, now for the really radical part. The phonon-less state itself, this isn't just better insulation. It's putting the qubit in a material pushed right to the edge, near a continuous structural phase transition. What on earth happens there?
Yeah, it's a wild idea. This brings in the soft mode concept, developed back in the 60s by Cochrane and Anderson. As a material approaches a critical temperature, Tc, a specific phonon mode, the soft mode has its frequency, cosine, drop anomalously.
Like the lattice is losing its springiness in one particular way.
Precisely. In fact, Haushoff squared goes like the distance to the critical point, Ttc. At Tc itself, Haushoff vanishes. The atoms basically freeze into a new structure, lower symmetry.
And this has been seen experimentally.
Oh yes, absolutely. Famously in materials like strontium titanate, subpartioses. But here's the crucial bit, the overdamped limit. As Haushoff gets very small, its damping rate can become larger than the frequency itself.
Damping is stronger than the oscillation.
Exactly, which means the atomic motion isn't really oscillatory anymore. It becomes slow, sluggish, diffusive, like trying to move through thick syrup. Spectroscopically, that sharp phonon peak just broadens out completely and merges into a wide central peak right at zero frequency.
A central peak at zero frequency.
That central peak is the definitive signature. It means the whole concept of a well-defined phonon mode, a nice oscillation, has totally broken down for that mode.
So the phonon-less state, it's not actually silent, it's just different noise.
Exactly. It's definitely not silent. The phonon quasi-particle model just fails. Atomic motion is still there, but it's complex, non-oscillatory, diffusive.
So energy still transfers, just messily.
Probably inefficiently through complex local processes, yes.
Yeah.
Not nice propagating ways. And a key nuance. This breakdown is often mode-specific. The soft mode goes overdamped. But other phonon modes, maybe the long-wavelength acoustic ones, the ones that represent overall vibrations of the crystal, they might survive just fine.
Ah, and if those are the ones causing the qubit decoherence?
Then the whole strategy is potentially pointless, right? You haven't gotten rid of the relevant noise source.
Okay, let's get critical. The idea sounds elegant on paper. Kill the phonon concept, kill the decoherence channel, boost coherence. But does it actually can out when you look closer?
Well, this is where we hit what's likely the fatal flaw. Just because you don't have well-defined phonon quasiparticles doesn't mean you don't have atomic motion. The qubit still feels the atoms moving.
It couples to the atoms, not our model of them.
Exactly. So while you might suppress the high-frequency noise, maybe improving T1, the overdamped soft mode creates this new, dominant, broad central peak right at pro.
Which means?
A massive increase in the low-frequency noise.
Oh, dear. And that hits T2 hard.
Devastatingly hard. Remember, T2 is sensitive to that low-frequency rumble, so it would likely plummet.
And T2 is often the bigger bottleneck for algorithms than T1, right?
Often, yes.
Yeah.
It limits the quantumness you can maintain over time. So this trade-off, maybe better T1 for much worse T2, looks like a net loss for computation. The environment becomes, in a way, more classical, not quieter. It's just really good at killing superposition.
So it's not just a theoretical noise trade-off problem, operating right at a critical point. That sounds inherently unstable. What other issues pop up?
Oh, it's incredibly unstable. You get a whole bunch of other noise sources, too, like critical fluctuations of the order parameter. Near Tc, the property that defines the new phase, like polarization, fluctuates wildly over large distances.
Terrible for a sensitive qubit.
Absolutely huge noise. Then there's just the messiness of real materials. Defects, strain, inhomogeneity. A lattice near TC is super soft, very susceptible to these imperfections. So you get a really non-uniform noise landscape.
Yep.
Each qubit sees something different.
Nightmare for scaling up.
Totally. And if you try to push this to absolute zero, a quantum critical point, QCP, well, that's a double-edged sword. A QCP is highly entangled itself, but the qubits' interaction can actually destroy the very criticality you're trying to use. The protector is as fragile as the protected.
This is sounding like a materials science and engineering disaster waiting to happen. Are there any materials that could even theoretically work? Could we build on them?
It's a huge challenge. We can talk candidates, but there's always a catch. Perovskite oxides, like SRTO, well-studied common substrates, show soft modes, but maybe not the most extreme phonon breakdown across the board.
Okay.
Others, halide perovskites, like CSB-ABO, very soft, lots of anharmonicity, sometimes unstable even in simple models, but they're often chemically unstable, ionic, hard to work with for devices.
So soft, but maybe too messy.
Yeah. And at the extreme end, superionic conductors, like QTO, they have almost liquid-like ions, massive anharmonicity, phonon picture really breaks down. But mobile ions, chemically reactive, exceptionally bad hosts for making precise, stable qubit interfaces.
So there's a fundamental trade-off, it seems. The materials with the most extreme phonon breakdown are often the least suitable for building qubits in the first place.
That's exactly the problem. And the engineering challenges on top of that, monumental. Maintaining stability at TC, say, to within microkelvin, across a whole chip, way beyond current cryogenics.
And dealing with real-world imperfections.
Right. Hysteresis, defects, surfaces, they all smear out that perfect critical point. And tuning it precisely with pressure or electric fields on an integrated circuit, not scalable.
And then there's the qubit itself. It's not passive. It has voltages, microwaves. How does it interact with this hypersensitive environment?
The hostile takeover. It likely defeats itself.
Yeah.
First, fabrication. Making atomically precise qubit structures, like Josephson junctions, on a material that's fundamentally unstable and about to rearrange itself seems practically impossible. You need pristine interfaces.
You wouldn't get them.
Almost certainly not. And second, even if you could build it, there's the operational perturbation. The qubit's own control signals, microwave pulses, DC biases create strong local electric fields.
And near a ferroelectric transition, the material is hyper-responsive to electric field.
Exactly. That local field acts as a symmetry-breaking field. It forces the material right around the qubit out of the critical region and into a stable, non-critical phase.
So the qubit effectively shields itself from the critical point it was supposed to benefit from.
Precisely. It defeats the entire strategy. It's like trying to study STAG by turning on a giant fan right next to you.
Wow. Okay. So, summing this all up, the idea of a phonon-less quantum computer. Intellectually fascinating, really audacious. But this deep dive seems to reveal, wow, profound and likely insurmountable challenges, both theoretically and practically.
Yeah, the verdict seems pretty clear. Based on what we understand now, it's just not a viable path towards fault-tolerant quantum computing.
Yeah.
You're trading a known, manageable, though difficult, decoherence mechanism for potentially much worse noise sources, especially that low-frequency stuff, all in a material platform that's incredibly difficult, maybe impossible to work with.
Seeking quiet by going to one of the noisiest, most unstable places in physics.
Essentially, yes. It sounds counterintuitive because it is.
But it's not a complete dead end in terms of learning, is it? This whole thought experiment, even if flawed for building a computer, must teach us something.
Absolutely. It forces us to really grapple with the environment in quantum systems, to move beyond those simplified Bath models.
What's the real legacy then?
Well, it raises fantastic scientific questions for theorists. How do you properly model a qubit coupled to that weird central peak noise? What are the exact forms of T1 and T2 then? How do correlated errors, which are bad for error correction, behave near a critical point in an array? These are deep questions. And maybe even more excitingly, it points towards using qubits as sensors to probe these exotic states of matter.
Turn the problem into a tool.
Exactly. Imagine using a qubit sensitivity to map out how that noise spectrum changes as you tune a material like SRTO towards its transition. Stick a spin qubit on top and measure its coherence.
Or use a tunable transmon to really map the noise frequencies in something like lead telluride, PBT, and compare it directly to bulk measurements.
Precisely. You get an unprecedented microscopic view of these complex dynamics.
So, while the Phonon-less quantum computer itself might stay science fiction, the journey exploring the idea could lead to genuinely new science, pushing boundaries in both quantum computing and condensed matter physics. It really makes you think about how fundamental these vibrations are. What stands out to you, our listener, from this deep dive? We hope this is giving you a shortcut to being well-informed and maybe sparked a new kind of curiosity about this incredibly complex, fascinating world hiding just beneath the surface of our quantum ambitions.